Quantum computing technologies and architectures are not the end, but perhaps it paves potentially the way to more profound development in the future of computing and information processing. An example could be the bio-based neuromorphic computing, which aims to mimic the structure and the function of the human brain to achieve more efficient and adaptive information processing. This comes with understanding more the quantum neuroscience and the neuromorphic computing. We have already very efficient biological quantum computer which works pretty efficiently. The human brain is a complex network of neurons and the synapses that process information through electrical and chemical signals. This could be the future of computing besides or as an extension to quantum computing. This year, Nobel Prize in Physics marked a significant milestone in the field of quantum physics and the foundations of quantum computing, where John Clarke, Michel Devoret, and John Martinis were awarded the Nobel Prize for their pioneering work on macroscopic quantum tunneling demonstrated in a superconducting circuit. This discovery not only deepens our understanding of quantum mechanics, but also laying the groundwork and the development of superconducting qubits, which are now among the leading technologies in the race to build practical quantum computers. So this makes us wonder how the future will look like regarding the computing technologies. There is need for fast and efficient computing since the development of analog calculators and then the development of digital computers. We have seen a rapid evolution in computing technologies. Now we have efficient, powerful classical computers with CPUs and GPUs that can perform billions of calculations per second. However, still simulating complex systems like molecular structure and molecular interactions still challenging for classical computers due to the exponential growth of the computational resources needed to perform such computations. This pushed several scientists in the 70s and the 80s, including Richard Feynman, to propose the idea of quantum computing, which leverages the principles of quantum mechanics to perform computations that are infeasible by classical computers. Hence, this pushed several scientists in the 70s and the 80s, including Richard Feynman, to propose the idea of quantum computing, which leverages the principles and the language of quantum mechanics to perform computations that are infeasible for classical computers. Hence, you simulate quantum systems by other quantum systems. In that sense, you leverage the quantum effects such as the superposition and entanglement to perform parallel computations and solve problems more efficiently. But how this could even be useful? Let's find out. I made a complete video about this. You can see it on the screen and in the description below the video about the history of computing and quantum computing. So I will leave this up to you, and now let's dive deep into quantum mechanics and the discovery of Nobel Prize. In a nutshell, quantum mechanics provides the language of microscopic world describing the behavior of particles at atomic and subatomic scales. It introduces concepts like the superposition, entanglement, and wave particle probability. In microscopic world, quantum effects are significant and observable. In macroscopic world, classical physics emerges as a collective approximation of quantum mechanics due to the presence of zillions of particles and interactions. Hence, we can describe everything that happens in our daily life using the approximated Newtonian mechanics and without the use or the need for quantum mechanics. Take this example. If you hit with a ball the ground, the ball will bounce to you every time. So this you can describe with Newtonian mechanics. If we take this example and have the analogy of this ball in quantum mechanics, it is a different situation. The analogy will be that when you throw the ball towards the ground, it won't bounce back every time. It might tunnel through the ground instead of bouncing back to you. In fact, tunneling would mean that the state density is still non-zero. In fact, tunneling would mean that the state density is still non-zero in the classically forbidden region. So it has a finite probability of finding the particle there. So if you have an electron confined in a potential well, still the electron has some probability to exist outside this well, and this is known as tunneling. So tunneling is manifested in the quantum world. Electron confined in a small region can tunnel through energy barriers that's impossible in the classical world. The Nobel Prize was awarded to the work that showed the ability to observe the tunneling effect in the macroscopic world. In 1984 and 1985, John Clarke and Michel Devoret and John Martinis developed electrical circuits with two superconducting components separated by a thin insulating barrier. In superconductors, charges can move without electrical resistance. Hence, in this specific experiment, it showed that the whole entire circuit can act as one single particle system. It means that the current can flow from one conductor to another without any voltage applied, and the current can tunnel through the insulating barrier. With that, they showed the quantum tunneling effect, in which the charges used to escape the zero voltage state and even generating an electrical voltage. Besides, the system now acts like an artificial atom. The energy of the system is quantized, meaning that it can only take discrete values just like an energy levels of an actual atom. The discovery highlights that with macroscopic object, particles can still exhibit quantum behavior, which was previously thought to be limited to microscopic particles and the microscopic world only. These experiments were the birth certificate for superconducting qubits. They provided the essential proof that you can build a quantum system on a chip instead of just finding one in nature, just by creating those artificial atoms using superconducting circuits. This system laid the foundation for the development of quantum computers using superconducting qubits, which are now one of the leading approaches in the race to build practical quantum computers. The idea is creating artificial atoms with superconducting circuits is all what you need to proceed. The qubit now is the fundamental unit of quantum information. It is analogous to the classical bit, but it can exist in a superposition states. So it can be 0 and also it can be 1, and it has the ability to be partly in 0 and partly in 1. So if you map this on a superconducting circuit or an artificial atom, typically you would need two distinguishable and stable energy levels to represent the 0 and 1 states, and the ability to manipulate and read out those states accurately. This was a breakthrough. It proved that a man-made circuit wasn't like a classical switch, like just 0 or on or off, but you can use it as an artificial atom with a ladder of a specific energy levels. Hence, we understand the following. With this circuit, if you map the qubit on it, you will need the ground state of this artificial atom or the lowest energy to represent the qubit state 0. And the first excited state or the next level to represent the qubit state 1. And hence we can call this a superconducting qubit. Superconducting qubits are made of simple oscillator circuits consisting of capacitors and inductors. Then they are cooled to sub-millikelvin temperatures, where it makes it superconducting and electricity can flow without resistance. Then it would turn into a quantum system where energy levels are quantized, as I mentioned before. However, the spacing is even. With the additional Josephson junctions, for example, you can introduce nonlinearity and create discrete energy levels which are uneven. So you can control them easily, and you can focus on the lowest two energy levels to represent the 0 and 1 without touching other higher levels. And after this, you can control the circuit with microwave pulses to perform quantum operations and also read out the qubit state by sending microwave signals to a nearby resonator that is coupled to the qubit. With this, Nobel Committee honors fantastic pioneering discovery of macroscopic quantum tunneling and the development of superconducting qubits, which are now a leading platform for building quantum computers. This is nice for the ending of the International Year of Quantum Technology 2025. We are now transiting towards the end of this year. We are now in October. So it is a good thing that Nobel Prize are also trendy. Last year was about AI, this year is about quantum technologies. Okay, that's great. Of course, quantum computing is still in its infancy, and are many challenges to overcome before we can build large-scale, fault-tolerant quantum computers. Such level would enable us of performing meaningful computations that surpass the capabilities of classical computers. For example, to perform chemistry simulations, you would need thousands of high-quality qubits with low error rates and long coherence times. And with these fault-tolerant quantum computers, we expect to be able to do such or some useful quantum computations beyond proof of concept use cases. And also we have to note that superconducting qubits are not the only technologies. We have now several quantum computing technologies and architectures, including superconducting qubits, which we have discussed already in this episode: trapped ions, topological qubits, photonic qubits, neutral atoms, and many more. Some of these technologies are more mature and have been realized, like the example I have mentioned in this episode, the superconducting qubits. It's worth mentioning that such technologies each has its own advantages and disadvantages regarding the scalability, the coherence time, 1 qubit and the 2 qubit gate fidelities, and the ease of control. I filmed a complete video about this, which will be released soon. So stay tuned for this video because it will show you in depth the benchmarking and the differences between the metrics of different uh, quantum or different quantum hardware in the market. So stay tuned. Okay, so we have now the Nobel Prize Committee is trendy. The last year was about AI. This year now we have about quantum technologies. Once we know this, we still wonder what will be next, what is beyond the quantum computing. No doubt that the knowledge we gain from quantum computing would help us in the future developments of quantum technologies. Also, we can benefit from this into the bio-based neuromorphic computing. Maybe this could be one of the upcoming Nobel Prizes. Who knows? One of the strong applications now is the brain-inspired computing systems that mimic the structure and the function of the human brain, potentially leading to more efficient and powerful computing paradigms. This is from a software and algorithmic perspective. There are some entities who offers bio-based hardware for computing that uses, for example, real bioneurons in laboratory dishes and so on. But there is, of course, significant ethical and societal debate and implications about this. But now we are discussing only the software and the algorithmic side. So by understanding the quantum neuroscience, how large molecular groups work together inside a particular neuron and how the neurons work together in a network to process information, we can develop more advanced quantum neuromorphic computing systems that leverage such a design and the quantum effects for enhanced performance. Hence, as Nobel Prize discovery showed, having a superconducting circuit that behaves like an artificial atom, that could be done the same. We can do the same. I mean, we can build a quantum systems which emulate the behavior of biological neurons and synapses at the quantum level and leverages such efficiency which we see already in the brain. Hence, the quantum neuroscience is not only important for understanding the brain, but also for developing new computing technologies that can harness the power of quantum mechanics for more efficient and adaptive information processing. There are active research and applications in this field already around, such as the spiking neural networks, the quantum-inspired algorithms, and the quantum machine learning. This is still from the software and algorithmic side. From the hardware side, in my opinion, there is need for huge effort to be made to develop quantum computing systems that leverages and that can emulate the work that's done in actual biological neurons and synapses in the brain. This could be the future of computing besides or as extension to quantum computing. I find this fascinating, don't you think? So please share your thoughts in the comments section below the video. I'm interested in this topic and in this file, and in the near future, I plan to develop and produce more videos and articles about the quantum computing technologies and the quantum neuroscience and the neuromorphic computing. So stay tuned and don't forget to subscribe and hit the notification button and the bell for this channel so you can find the upcoming videos. Until then, see you.